So we're going to examine limits at infinity for rational functions. And the main issue for rational functions, you've got a polynomial on top and a polynomial on the bottom. So which one is growing faster? As x gets bigger, is your numerator or your denominator getting bigger faster? Because that will determine whether you have a limit that exists or you don't. So we have a procedure that we're going to go through first here and talk about how to use it and practice using it. And then after we do that, we're going to see if we can't kind of use some intuition to come up with a shortcut or a shorter way to determine. So here's the procedure. We'll write it out in words first, and then we'll use it. So we're going to start and divide every term in both the numerator and the denominator. Oops, I can't spell numerator. So it happens if you talk while you're trying to write. Numerator and denominator by the highest power of x that occurs in the denominator. Okay, so there is a choice here. On this first step, you've got to choose the correct power of x. And it's the highest power of x from the denominator, not from the whole thing, but just from the denominator. So the reason you're allowed to do this is you're basically like taking your fraction, which was a p over q, and you're multiplying it by like 1 over x squared, 1 over x squared, and distributing that to all of the terms inside, which is effectively just dividing everything by x squared. So that is why we're allowed to do that. It's not changing the value of the expression. Then you're going to simplify each term. Oops. Simplify each term. And here's where our useful fact comes in. So we're going to use the fact that, remember, the limit as x approaches either positive or negative infinity of any constant over a power of x is 0. And that will basically eliminate any term with an x still in the denominator, because its limit is going to be 0. And then we'll use limit laws for the rest. Okay, so we're going to try it. I have 3 problems that we're going to try. And we're just going to go through this procedure. Now, before we apply it, I just want to take 1 second to go back and talk about when do I use this procedure? A lot of these videos we go through, here's how to do it. But you have to make sure you're also studying and paying attention to, wait, what am I doing? When am I doing it, right? So I'm trying to find the limit as x approaches infinity or negative infinity of a rational function. So I come to this example. I have the limit as x approaches infinity, and this is a rational function. So that is the time to apply this procedure. So I see that my highest power of x in the denominator is x to the third. So I am going to keep my limit in front. You got to keep your correct notation until you actually find the limit. You keep that limit notation in front. So we're going to divide everything by x to the third. Now you don't necessarily have to write that step every time, but at least for this first one, I wanted to make it clear that that's what we're doing. That didn't work out so well. Keeping my limit notation in front. Now I'm going to simplify. So I'll have 7 over x minus 2 over x squared over 4 minus 6 over x cubed. Okay. So those are the first kind of 2 steps, dividing everything by the highest power of x in the denominator and then simplifying. And then in the next step, I'm going to actually take the limit. And I often just write kind of like this. I'm indicating through these arrows that each one of these terms is going to fall under that constant, this limit right here, constant over x to a power, the limit as x goes to infinity or negative infinity. So each one of those, the limit will go to 0. So what I'm left with is just that 4 in the denominator. And so the numerator will go to 0, the denominator will go to 4, and so my limit will be 0. So let's do one more together. I'm looking at this one. I'm taking a limit as x approaches negative infinity of a rational function. So that is what indicates to me that I want to use this procedure. The highest power of x in the denominator is x. So I'm just going to divide everything by x. Like I said, you don't have to write this first step. I find that just for kind of keeping track of everything's sake, it's not a bad thing to do. So then I'm going to simplify. And then I'm going to evaluate the limit. And again, anything that has an x, left in the denominator is going to go to 0. So this limit will be 9 over 2. So go ahead and flip to the next page, pause the video, and give that one a try. Okay, so doing the same thing, taking the lowest power of x in the denominator, dividing everything by x. And when I simplify, I end up being able to eliminate the 2 terms with the x still in the denominator, but I also have a term in the numerator that has an x still in it. So as x goes to negative infinity, the numerator is going to get really, really, really big because it'll have a -3 times a very, very small negative number, which will go to infinity. Now, there is an observation we can make here. Notice on this one, the power in the numerator was higher than the power in the denominator, and that gave us an x left over in the numerator, which caused the limit to go to infinity. If we look at the 2 that we did on the previous page, here the powers of the numerator and denominator were the same, and so when we divided by that highest power, we ended up with just these leading coefficients as constants, and so that was the limit. And last but not least, in the first one, the power in the denominator was higher than the power in the numerator. So when I divided by that x cubed, everything in the numerator ended up going to 0. So our entire limit went to 0. So there is sort of a pattern that you can see there. We're going to write it in this box. The end behavior of a rational function matches the end behavior of the quotient of the highest degree, basically the leading term, the highest degree term in the numerator and the highest degree term, or the leading term, in the denominator. So I'm just going to go back to each one of these, draw a little line here, and you can see if I take the limit as x approaches negative infinity, and I just use the highest degree terms in each numerator and denominator, I can cancel that 1x. And that's exactly the same limit that I had right over here. Okay. And so it's kind of a shortcut. You don't necessarily have to go through, if it's a rational function, every single one of these steps. You can just look at the first two terms. Well, I shouldn't say first, the two highest, the two leading terms, right? So again, just a quick view of those leading terms. And if I did this limit using just those two terms, then I could cancel again the x squared on top. And then now I have a constant on the top and an x on the bottom, which we know goes to 0. And you could fill in the same thing for number 2 here, and you would end up with the x's just canceling, and you get 9/2 again. So that the reason that that shortcut works is because of the process. You might not be able to do that if it's not a direct, like polynomial over polynomial. So anytime that you're dealing with like a e to the x or something, you might just have to do a different technique. But for the straight rationals, that will work. So now we're also going to talk about rational functions that contain radicals. And so one of the reasons we learned this technique is because it doesn't work perfectly if the functions have radicals in them. Okay, so let me give you an example. On the next page, you can see we're trying to find limits at infinity of these types of problems. Okay, so there's two things that come into play in order to do those. We are going to apply the same technique, okay, but we have to keep in mind what's happening when we're square rooting something squared. Okay, so we're going to start by recalling that the square root of x squared is not just x. It's the absolute value of x, which we know to be a piecewise function. So let's just take a minute to convince ourselves that this is true. If I start with a negative number and I put it in here, I'm going to square it. So -3 squared is 9. This tells me the positive square root. So the positive square root of 9 is 3. So if I started with -3, I put it in here, I'm going to get out 3, which is the opposite of what I started with. Okay. And if I plugged in 3, I would just get itself 3. Okay. So we have to keep in mind that when you square root something squared, if the thing you started with is negative, what you're really getting is its opposite. Okay. And then here's how we're going to apply that to finding limits at infinity of rational functions. So when x is approaching positive infinity, we're talking about positive x's. So the square root of x squared is just good old x. Okay. However, when you're approaching negative infinity, now you're in negative numbers. So the square root of x squared is now going to be negative x. Okay. And so in this situation, if you divide an x, or I should say, if you divide not an x, by x outside of the radical, it must be negative x. And we're going to show you in an example in just a second. Okay, and then the other thing that's important to realize is the powers, right? So the power under the radical is double the power outside the radical if you're keeping things equal. So just look at the example I have above here, right? The square root x squared, so in the radical it's x squared, but once it comes out of the radical, it's half of that. So that's what we're just trying to make sure we point out. So let me go through and show you a couple of examples, and I think that will help these make a little bit more sense. We're going to do the same function twice, once as we approach positive infinity and once as we approach negative infinity. Okay. So here we are approaching positive infinity, and then we look at our highest power of x in the denominator. So it's x squared, but it's under a square root. So what power is that truly? It's a square root of x squared. So if we're dividing underneath the radical, that would need to be an x squared. But when we divide outside of the radical, it's going to have to be just an x so that those powers are the same. So we have highest power is x squared under a square root. Okay. And so that becomes positive x outside the radical because we're approaching positive infinity. So as we go to fill in our limit as x approaches infinity, I'll start with that denominator. So I have this big square root, and everything under the square root is going to get divided by x squared because that is the highest power, x squared under the square root. But when I come to the numerator, this does not have a square root anymore. So in order to divide it by the same power, I need to divide it by just x to the first. And it's going to be a positive x because we're approaching positive infinity. Okay. All right, so a little simplification. I have 3 minus 2 over x over the square root of 2 plus 1 over x squared. So we see that we have a couple terms that'll go to 0, and I'll be left with just 3 over the square root of 2. Okay. Now, how does that change when we go to do the second one? So now I'm approaching negative infinity, but I have the same function. So my highest power is x squared, again, under the radical. But because I'm approaching negative infinity, this becomes negative x outside the radical. And that's because we're now approaching negative infinity. Okay. So it's going to look almost identical, except for when I get to the numerator, I'm going to divide each one of those terms by negative x. It doesn't look any different underneath the radical because it's an x squared. So I now have a negative 3 up top. I guess I could write that as plus 2 over x. And I have the same denominator. The same two terms are going to approach 0. And so it's a very similar answer, but now it's negative. Okay, and I have one more example here. You'll notice that this is not a rational function. Okay. But the problem is, if I think about plugging in infinity, which is kind of a weird thing to do a direct sub with, I would have the square root of basically infinity, which is still infinity. It's smaller, but this is going to be really big. And then I'm subtracting something else that's really big. So I have infinity minus infinity, which we can't say anything about. We're going to learn this more in the next lesson, but that's another indeterminate form. If we had infinity plus infinity, then our answer would just be infinity, but we don't. So in this case, what we're going to do is we're going to turn it into a rational function so that we can apply this method by multiplying top and bottom by the conjugate. So this conjugate method is back, and it's basically just a way to turn this into a rational function that we can then analyze, because as it's written, there's not much we could do with it. So if I'm going to use my difference of squares when I multiply this out, my numerator will be 9x squared plus x minus 9x squared. Those things will clearly cancel. So the 9x squareds cancel. So I have just an x in the numerator and then this in the denominator. So we're going to apply this again, the same technique. Our highest power in the denominator, we have an x squared under a square root. So that's like an x to the first, which is the same as plus 3x. So we're going to divide by an x squared under the square root. Because I'm approaching positive infinity, that will just be plain old x on the outside of the square root. So x over x, 9x squared over x squared, x over x squared, and 3x over x. So let's see, what's going to cancel? This is, looks like the only term that's going to be left with an x in the denominator. And everything else will just be a constant. All right. So that is our technique for applying limits at infinity to rational functions, including those with radicals.